with this, Robert, the floor is yours. Go ahead. We are looking forward to your talk, and thanks a lot in advance.
Okay, thank you. So you can hear me and see the slides?
Perfect.
Perfect. Okay. Then, yeah, hello also from my side to everyone. My name is Robert Zimmerleiter, and I'm going to talk today about accurate standoff temperature measurement using cost-efficient MEMS-based near-infrared spectroscopy, a spectrometer technology. So, first of all, I want to shortly talk about what temperature actually is and why it is important for us to measure it. So, temperature is usually measured in the unit Kelvin or degrees Celsius, and actually describes the average kinetic energy per molecule, atom, or other particle in a substance, and is very different from heat, which is the amount of energy transferred between objects at different temperatures. I just say this because it's often mistaken for one another. So just the thermodynamic definition of the temperature very formally is the partial derivative of the internal energy with respect to the entropy at a constant volume and number of particles in the system. Temperature is also part in the very famous and important second law of thermodynamics, which is written here in the center. I don't know if you can see my mouse actually, or do I have to use a laser pointer? So now you should actually see it. So it is also part of the second law of thermodynamics, which famously states that heat can never pass from a colder to a warmer body without you investing some additional energy in it. This is also illustrated in this picture on the right side. But what for us is more interesting is what does temperature actually do? So the temperature has a very, temperature and also actually heating and cooling rates have a very, very strong influence on many parameters and properties in a system. This includes, for example, the rate and speed of chemical reactions. They usually go much faster when the temperature is higher. Also the rate and speed of physical reactions, such as the drying rate in a system or the mixing rate of certain substances, is strongly influenced by temperature, and other material properties that might be of interest, such as the aggregation state. Of course, everybody knows if you cool water down, it gets solid at some point and it's liquid at normal temperatures, and it gets gaseous if you heat it over 100 degrees. You also have oxidation states that depend on the temperature in the system. The microstructure of different materials can change whether you heat it fast and cool it down fast, or at different temperatures. Also the microstructure might be different, and also viscosity, and many, many more. So importantly, the accurate temperature measurement and control of the temperature can, for different processes, significantly improve both the product quality and also, importantly, especially nowadays with high energy prices, the process efficiency. So how to measure the temperature? Over the last, I would say, many, many decades, many different methods have been developed to measure the temperature of a system. These methods usually rely on changes in material properties that we know how they behave with temperature, and these are used to measure the temperature, such as the change in volume or length. This is famously used in glass thermometers, which were used with mercury, but nowadays are usually filled with alcohol. You also have gas thermometers. Both of them use the expansion of a liquid or gas with increasing temperature to give you a temperature reading. You have also bimetal mechanical thermometers. You can also see this in the little GIF animation here, how it reacts to the heat of a lighter. You have two different metal stripes that expand differently with temperature change, and therefore you can get and make a very cheap and efficient thermometer out of this. You also have some devices that rely on electrical potential or resistance change with temperature, such as thermocouples that are widely used, resistance thermometers, also PTC and NTC thermistors. Some thermometers rely on pressure changes, such as the vapor pressure thermometer, gas pressure thermometer, and there are many, many more. And I don't have enough time to name them all. But for most of these measured methods and for all of the above, it's true that you have to have a sensing element that must be in direct contact with your sample that you want to measure the temperature of, which is in the industry often not possible or desirable. So there's another way to measure the temperature of a body without actually touching it. This relies on the detection of thermal radiation that is emitted from the sample surface, which is often referred to as a black body radiation. So the theory states every object with a temperature above 0 Kelvin, which is the absolute zero, emits electromagnetic radiation from its surface to a certain degree, which is in the idealized case given by the famous Planck's law of blackbody radiation, which is also illustrated in the graph on the right. You can see the formula on the top right, and there's some different emission curves for different temperatures for an ideal blackbody are drawn for temperatures, for example, 6,000 Kelvin or 3,000 Kelvin. And we can see the hotter the object, the more radiation it emits. So when you have very hot objects like the surface of our sun, we have a significant portion of the emitted radiation in the visible range, which gives us the sunlight that we need so urgently. But if you cool down to lower temperatures and go more and more to temperatures that you usually want to measure in measurement applications, you see that the infrared portion towards the right of the graph gets more and more important. And this is why the infrared spectral range is usually used for this kind of measurement. Two other important laws that can be derived from the Planck law of blackbody radiation is Wien's displacement law, which basically gives you how the wavelength of the maximum emission changes with the different temperatures. This is also shown in the graph where this blue line, which you can see is curved towards the right with lower temperatures. You get the emission maximum at longer wavelengths. And you also have the Stefan-Boltzmann law, which gives you how the power of the total radiation that is emitted changes with the temperature, which is the fourth power of the temperature. So the most important thing to know is that the power, both power and wavelengths of the radiation that are emitted from an object's surface at a certain temperature, the power and wavelengths are very strongly influenced by the surface temperature of an object. So if you change the temperature, not only the power will change, but also the wavelength and the distribution of intensity across the wavelength scale will change significantly. So just a little bit more of this blackbody theory. The blackbody is a very idealized theoretical object, absorbing all incoming radiation and allowing no reflection or transmission of electromagnetic radiation, which means emissivity and absorption are both equal to 1, which is not the case for real life objects. A better approximation for real life objects is actually the so-called gray body, for which we allow some reflection to happen, and we get the sum of the emission and the reflection is equal to 1 for the mostly valid case that the transmission in the infrared can be neglected, which is true for most materials. So actually the better approximation for the emitted thermal radiation is the gray body, which is then given by this formula down here, which is basically the blackbody radiation scaled with the emissivity of the material epsilon, with the value of epsilon being between 0 and 1. This also influences the Stefan-Boltzmann law in the same way. And we will later see that the epsilon actually has a strong influence on some contactless temperature measurement methods. And it also actually varies for different materials and also different surface structures of materials very strongly, and can give you a very hard time when you want to measure the temperature without touching the sample. So here we see a schematic setup, which we can use to optically measure the surface temperature of an object. We have the object itself on the very left side. We use some optics to collect the radiation that is emitted from the object. Then we couple it here into an optional optic fiber, which delivers the signal to our optic sensor. Alternatively, you could also couple the light directly into the sensor, but for convenience reason, and sometimes also for protection of the sensor, it's often much better to use an optic fiber, which you can use for a couple of meters, many meters even in the industry, to get your sensor to a safe position, and you can guide the light towards where you need it. And as we can see, a sensor and object sensor and optics are both not in direct contact with the measured object, which is the nice thing, but it only collects the emitted radiation via suitable optics. This brings several advantages compared to measuring in direct contact. It allows the temperature measurement of samples that are either moving, very hard to reach, and or very hot. We also have very fast measurement and response times. The measurement does not influence the measured object at all because it's not in physical contact. The measurement is completely non-destructive, and also we have no wear and tear of the measurement position, leading to increased longevity. So there are now different sensor options that can be used that I want to shortly describe to you. So the first approach to measuring the temperature contactlessly via optical methods is the integrative measurement, which is usually used in so-called one-color parameters. Usually they are just called parameters. So what these devices do is they measure the radiation emitted from a sample in a certain wavelength window, which is typically somewhere between 1 micrometer and 14 micrometers, and it measures the total intensity in this range. So this is also drawn schematically on the left side. Here we can see a simulated blackbody spectrum. And what the sensor does, it is measures the area under this curve from the starting wavelengths to the finishing wavelengths, lambda 1 and lambda 2 here. So the signal of the sensor will be proportional to the integral of the intensity as it depends from lambda with respect to lambda. So the area under this curve. Basically, this sensor signal in the ideal case should be proportional to the temperature of the sample surface. Since, as we saw with the Stefan Boltzmann law, the hotter the object is, the more the radiation it gives off and the higher the sensor signal. So these sensors have advantages and disadvantages, as everything in life. There is the low-cost hardware, as you can realize, very, very low-cost sensors this way, and you can make very compact sensors as well. But in this case, we have very strong disadvantages that often hinder the use of this kind of measurement for industrial application. Namely, the temperature reading is very strongly influenced by the changes of the emissivity epsilon. Since the emissivity directly scales the amount of radiation that the sample gives off, and this sensor exactly sees the amount of radiation that the sample gives off. Depending on the emissivity, it will see different temperatures. So if you have a strongly emitting material at a certain temperature and another material that is less emissivity at the same temperature, it will tell you the one with the higher emissivity is much hotter than the other one. Also, for the same reason, changes in absolute intensity directly change the measured temperature. So if you have different optics that collect more light, or if you have some fouling on the optics that reduce the light that reaches the sensor, this will directly influence the temperature reading that you get. And also many other influences from the surroundings, such as dust or whatever, or outside radiation sources that you might have in your environment, really directly influence the temperature reading and can give you very, very wrong readings in the worst case. So the much better approach is to actually use a 2-point measurement, which is used in so-called 2-color parameters. These kind of sensors measure the radiation emitted from a sample in 2 distinct wavelength windows. This is also schematically drawn here on the left side. We have wavelength 1 and wavelength 2. And the signal that the sensor gives off is then basically the ratio between the intensity at these 2 wavelengths. And this has the advantages that the absolute intensity does not have a direct influence on the measured temperature, since it influences both wavelengths in the same way and it cancels out in this calculation. Also, the influence of the emissivity epsilon can be at least significantly reduced, since if the emissivity at both wavelengths is same and constant, which is not always the case, but often, it cancels out in this calculation as well and gives you a steady and a constant temperature reading, even if the emissivity slightly changes. But there's also downsides, of course, if there are wavelength dependent changes in the emissivity, for example, due to changes in the surface structure of your sample, it can still give you false readings, and you wouldn't know if it does because it can't give you any other information than just the temperature and the absolute intensity. And the heat radiation from surroundings, if they are strong enough, they can also lead to very wrong temperature measurements, because heat radiation from surroundings might also just influence one of the wavelengths, one of the intensities at one of these wavelengths stronger than the other, and this will give you a very wrong ratio between the two and give you a wrong temperature. And what another downside is that the measured wavelengths are fixed in your sensor, and they're usually chosen to be very suitable for only a very limited temperature range. So you have no flexibility there. So there's a third option, which is basically the spectral measurement, which you can do with any spectrometer, where you measure the radiation emitted from the sample, not at only 2, but at multiple, up to several hundred different wavelengths. So what you get is a reading at a certain number of different wavelengths, and the signal that you get from your sensor is then a function of the intensity at all of these wavelengths. The temperature in this way can be calculated in different ways from the measured intensities. So you could also just emulate the other types of sensors by just using 1 or 2 or all of the wavelengths that you measured. And with this kind of data, you have much more available data, so you can further reduce the influence of the emissivity changes, since you can also choose how to evaluate the data and what wavelengths you want to use. The large number of the measured wavelengths allows you to measure a broader temperature range that you usually can with these 2-point or single-point parameters. And also, what is a very important point is that the shape of your spectrum, since you have so much data, you can actually get information about the measurement quality out of your spectral data. So you will see when analyzing the spectra, you can see if you measured a correct temperature or if you measured something else that might be influenced from the surroundings that you don't want to measure. And also the infrared spectra allows to gain further knowledge about the sample, for example, about oxide layer growth or other chemical changes on the sample surface. Of course, there's downsides. Depending on the hardware, the measurement times can be a bit longer than for parametric measurements, up to the second range. Depending on the hardware, there's always faster and slower options available. But what is mostly the deal breaker for this kind of measurements is the higher hardware price. So this is where actually these MEMS-based spectrometers come into play. While for conventional process spectrometers that were in the past used for this kind of measurements, you can pay easily up to 40,000 or above 40,000 euros. There's also the alternative of using compact, low cost and rugged MEMS-based infrared spectrometers, schematically drawn here also with a little size comparison. And here you can see one of these devices compared to a €2 coin. And these devices go for a price that is about at least a factor 10 lower than the big brother spectrometers, let's say it like that. And this is a very new technology. RECENT was amongst the first worldwide and the first in Austria to use this technology sometime in the last decade. But since then, a lot has been done in this field. And there's nowadays many options of different MEMS-based spectrometers from many different manufacturers on the market. Usually, a lot of times they are used for chemical monitoring or process analytical technology applications, also consumer applications, but some of these devices are actually also suited for contactless temperature measurement, which I want to show you today. So in order to show you, I like to discuss a measurement example that we carried out in our laboratory with one of these devices. This measurement was carried out in a dilatometer on a steel sample in vacuum. A schematic drawing of the setup can be seen on the bottom left. We have the sample, we have some cooled heating coils that inductively heat this steel sample. We do a reference measurement and temperature control using thermocouples welded to the sample. You can see this here in the zoomed in picture on the very right, where the thermocouples are welded onto the hot steel sample. A photograph of the dilatometer with the lid open is shown in this image. You can see the window also in the schematic. It's an infrared transparent window. Outside of it, we have the optics and an optic fiber guiding the light to the sensor. And the near-infrared radiation was measured using this sensor. And I want to show you the 3 different sensing methods, namely the integrative measurement, the 2-point, and the spectral measurement. And all of this data that I'm going to show you now was measured with the exact same setup. So there was no change in optics or in heating or in thermocouples or anything. So this data, in order to give a better comparison, was taken with the exact same setup. So first of all, I want to shortly discuss the integrative measurement. So this was done by just measuring the intensity that was given off by the sample in a wavelength range between wavelength 1 and wavelength 2. So the signal is just the area under this curve, which correlates to the integral you're seeing here on the top right. So in the graph on the top left, we see the experimental data for the calibration. On the y-axis, we see the temperature that was measured with the thermocouple. On the x-axis, we see the sensor signal that the sensor gave off. And we see the blue dots are always collected data points. So we measured from 500 degrees to 1000 degrees, always 50 degree steps. And this is how the sensor signal correlates to the temperature of the thermocouple shows. So from the Stefan Boltzmann law, you would just assume that the intensity that we measure is proportional to the fourth root of the temperature. But in reality, since we don't measure the whole spectrum from wavelength 0 to wavelength infinity, for which this Stefan Boltzmann law holds, we actually get a different correlation, namely with the 3.21th root of the temperature, which actually fits quite nice and gives us a root mean squared error for the calibration of about 2.33 degrees, which is probably mostly influenced by the non-uniform heating with the coils of the sample. So the sensor actually sees a spot and measures the average temperature in this spot, while the thermocouple that was welded on measures at a slightly different point, and we have non-uniform heating. We also have the error of the thermocouple. So this all amounts to, coupled of course with some of the optical errors, it amounts to about 2.33 degrees on average over the whole temperature range. So when we now use this calibrated sensor and make a validation measurement, this was done basically by removing the sensor, opening the lid of the dilatometer, changing the sample, closing, reattaching the sensor, and then doing the measurement again. We get some validation data, which is shown here in orange. Here we can see now the temperature of the thermocouple on the y-axis and the temperature that was calculated from the measured infrared signal on the x-axis. And the ideal case would be that they are perfectly the same. This is the black x equals y line. And we can see in blue the calibration data gives us the already 2.33 degrees Celsius that we already seen, but the validation measurement shows a very large error of about 18.67 degrees Celsius on average, which is due to most likely two different reasons, namely the emissivity epsilon might be slightly different because it's a different sample and a different surface structure. So the emissivity might change a little bit, and this directly gives you a false temperature reading. And also, since the sensor was detached and reattached to the dilatometer, changes in the orientation between the optics and sample might change the absolute intensity a little bit, and absolute intensity changes for this kind of measurement directly influence the measurement value and therefore give you a much larger error than you would expect. So the second measurement example is the 2-point measurement, where we actually took, as I explained earlier, the intensity as at two different wavelengths and calculate the ratio. And here on the bottom, top left, we have the experimental data, where again temperature of the thermocouple is plotted against the sensor signal, this time for the 2-point sensor. So here's the ratio between the two intensities, and we can see it's almost a linear correlation. We only have some slight non-linearities, which we take care of by using a polynomial data fit, which will serve as a calibration curve for our sensor. Again, we use this calibration curve to predict the temperatures for the validation data. And here we get a much lower error. It's already reduced from above 18 to about 10 degrees. And this reduction of the error is most likely due to the influences of the changing emissivity. They are now strongly reduced. So only the wavelength dependent changes in the emissivity now give you a slight offset in your readings, and the absolute intensity is completely removed due to the calculation of this intensity ratio, which also leads to much more precise measurement values. So now to the most important point, so the spectral measurement. So the measurement was also done in by collecting the whole spectral data from 1300 nanometers to 2600 nanometers. The raw spectral data you can see here on the graph on the top left. The lines go from the lowest temperature, 500 degrees Celsius, to the highest temperature, 1000 degrees Celsius, and they are color coded. And each step between the lines is about 50 degrees Celsius. Here we again can see the Stefan Boltzmann law in action. You can see with higher temperature, much more intensity is reaching the sensor. And now from this spectral data, we have different ways of calculating our temperature. So the first I want to shortly talk about is to fit the fitting of a gray body spectrum to the acquired near-infrared spectra. We know that our sample inside should behave more or less like a gray body given by this formula. So what we do now is we take the spectra that we acquired and the reference temperatures and use it for a sensor calibration. So basically we calculate a black body spectra from these sensor curves. And with this sensor calibration, we can then measure new spectra and then fit the gray body formula to it and get an exact value for the temperature that we would expect. So by using suitable fitting algorithms, you can extract from spectral data, you can extract the temperature by just fitting the gray body radiation to it. So this is what we did. First, for the calibration data set, we have the experimental data here, the temperature of the thermocouple on the y-axis and the temperature that we get for the calibration data using the fitting routine on the x-axis. Again, we get a comparable root mean squared error for the calibration of just below 3 degrees Celsius, mostly influenced by non-uniform heating and error of the thermocouple. And when we use this calibrated sensor to predict the values for the validation data set, we can see it fits very nicely. And again, the error is further reduced compared to the 2-point measurement. Since we have more data available, now we have an error of roughly 7 degrees compared to the 10 degrees we got earlier. It's a degrees of about, let's say, 30% lower error. And the main reason is that the influences of the emissivity and absolute intensity can further be reduced down, just because we have more data points available that we can use to estimate the temperature. And I just want to point out another very important feature of this kind of measurement, namely that the quality of the fit gives you a nice estimation of the precision of each measured temperature. So just by fitting newly acquired data with the gray body, with your sensor calibration, you get an idea how well it fits. And then this will tell you if you measured correctly or if there's some influence that you maybe didn't take into account, maybe some outside radiation sources that you were not aware of in your measured signal. And then you can actually get a warning out of the sensor in the best case. So another measurement example, how to extract temperature from this acquired spectra is to calibrate a model from the near-infrared spectra using machine learning algorithms. For this spectra, usually pre-processed. Here in this case, I show on the top left SNV normalized spectra, which completely removes the absolute intensity and shifts the focus more on the spectral shape of the spectra. Here we can see the veins shift rather clearly from blue to red. It shifts towards shorter wavelength. And here you just feed the acquired spectra and the reference temperatures into your machine learning algorithm and calibrate the model. This model then you can apply to newly measured spectra and get a temperature reading out of it. So when we do this in practice for the calibration data, here again, thermocouple temperature on the Y, temperature from the spectral measurement for the calibration data on the X-axis, cross-valid, the average error for the calibration is again roughly 3 degrees Celsius. And when we apply it to newly measured data, we again can bring the error down to under 5 degrees Celsius with this method, which is the lowest achieved validation error in this case. And since the machine learning algorithm actually relates signal changes to the temperature changes and allows therefore to minimize the measurement error by also blocking out other influences that you might not have taken into account earlier. And additionally, spectral pre-processing methods, which are an important part of these machine learning algorithms, such as the previously shown SNV normalization, eliminate unwanted influences, such as absolute intensity or other influences. And also, as before, the machine learning algorithm also allows estimation of the precision of each measured temperature by giving you statistical values of how good the spectra fit to the expectation of your machine learning model. So with this, I'm on my last slide, which is a short comparison of the results of this measurement example and a short summary. Here we can see the calibration error and validation error of the different measurement techniques. The calibration error is always pretty much constant, as I said, mostly in your non-uniform heating and error of the thermo element, of the thermocouple. And the validation error shows a clear trend that the integrative measurement or 1-point measurement is the worst. 2-point measurement is already much, much better. Still, the spectral measurement using a fitting routine can reduce the error a little bit further, but the best results we got actually with the spectral measurement using machine learning algorithms, which can minimize the error of the validation down to just below 5 degrees Celsius. So in summary, I hope I was able to convince you that near-infrared spectroscopy is a powerful tool for standoff temperature measurement and offers some advantages compared to conventional 2-color or 1-color pyrometers, such as a larger temperature range that you can cover when broadband spectrometers are used. You can use additional information that you can extract from the collected near-infrared spectra that give you information about the chemical composition of your sample, for example. And the measured spectra also give information about how trustworthy the measured value is. So you can actually implement warnings or ignore values that are not trustworthy enough according to your acquired near-infrared spectrum. And also you have a high flexibility regarding which and how many wavelengths you want to consider for the measurement. You can also go the extreme way and just emulate the 1-point or 2-point measurement in parallel with your spectral measurement and then see which one fits best. And another important point is that nowadays modern MEMS-based near-infrared spectrometers allow you to measure full near-infrared spectra already at a comparable price as you do with the 2-color parameters. So with that, I want to thank my colleagues at the Infrared and Raman group at RECENT and also our funding agencies. And of course, I want to thank you for your attention and I'm open to questions. Thank you.
Thank you so much, Robert, for this talk, for guiding us through theory and practice of temperature measurement.